Okay, I'm now going to look at question 11. So question 11 is a vectors question. So the first part is finding an equation of a line. So we want to find the vector AB. So this will give us a direction vector. So 2, minus 2 and 1. So the equation of the line, we've got x is going to equal, this becomes the coefficient of the x of the parameter, and then for the constant we can choose either of these points, so we'll choose point A. Y is going to equal minus 2t, take 2, and z is going to equal t plus 4, where t ranges over the real numbers. Okay. The second part, we want to combine the equations, the parametric equations we found for L1. We've got these Cartesian equations for L2, and we want to find out when L1 and L2 intersect. So to do that, what we're going to do is substitute these parametric equations into these equations here. So substituting parametric equations into L2. So the first case we get, now I'm going to compare these two. So we've got 2t plus 4 subtract 3 is equal to we've got minus 2t take 2 on 2, therefore 2t plus 1 is equal to minus t, that becomes minus 3, therefore 3t is equal to minus 4, and we should end up with t equals 4 on 3. Okay, so substituting that back into there. Okay, oops, made a bit of a mistake back up here, so let's just quickly correct that. That should be t minus 2 over here, so that becomes minus 3, so t equals minus 1. Substituting that back into the parametric equations, we've got x is equal to 2 times minus 1 plus 4, which is equal to 2. Y is equal to minus 2 which gives us a value of 0, and a z will be t plus 4, so minus 1, therefore point of intersection is 2, 0, 3. Now I should just go back and check the other pair here, just to make sure that we've got a consistent answer. So what I want to check is make sure that when I take this pair I get the same value of t. So I'll just put checking. So y was minus, oh, there we go. So minus 2t take 2 minus 2 over 2 is equal to t plus 4. So t plus 4 minus 5 all divided by 2. Let's cross out those 2's. So therefore minus 2t take 4 equals t take 1. Therefore let's just check that we haven't done something wrong here. Minus 2t, take 4 equals that's right, therefore t equals minus 1, which is consistent with what we got for the previous value. Okay, so we've found out where those two lines intersect. The next part, we need to find out the Cartesian product of these two vectors. So we'll call that V. Okay, so just working that out. So what I'll do here is I'll cover up this column, this row, and I cover up this column, move to the next column, so 1, 2, and then back around to the beginning again, 2, 1, plus k times 2, 1, minus 2, 2. So that's minus 4, so we've got minus 6i, take 3j, plus 6k, back into coordinate form, gives us that value there for the vector. Okay, well now we're going to actually use this. So we notice that these two vectors actually correspond to the direction vectors of line 1 and line 2. So we're going to use that information. So we've got 2 minus 2, 1 is the direction vector for L1, and the other one, 1, 2, 2 for L2. Therefore N is the normal for the plane containing L1 and L2. So our equation is going to be of the form minus 6x minus 3y plus 6z equals, and we know that those two lines meet at 2, 0, 3, so we can go minus 6 times 2 plus minus 3 times 0, 6 times 3. So that's going to be minus 12, there's a minus there, plus 18. That's plus 2. And finally dividing through by 3, so we end up with 2x plus y, take 2z, is equal to minus 2. So we'll say dividing by minus 3. And there you are, we've got it. So again, we've got a linkage between C part 1 and C part 2 happening there. Right, so show in part D1, we want to show that this plane, so normal vector 1 is 1, 0, 1. Normal vector for the other plane is 2, 1, minus 2. And if we can establish the fact that their normal vectors are perpendicular, i.e. that the dot product is 0, then that's good enough to show that the two planes are perpendicular. So left hand side of that is 1, 0, 1, dot product with 2, 1, minus 2, which equals 1 times 2 plus 1 times minus 2, which equals 0. So therefore are perpendicular to each other. Alright, so for this one what we want to do is work out the equation of the normal to the plane that passes through this point here. So we've got x is equal to s plus 5, and substitute that into the equation of the plane. So we've got s plus 6 equals 5, therefore s is equal to minus 6, therefore x is equal to 0, y is equal to minus 4, and z is equal to minus 1. So D is the point 0, minus 4, minus 1. Alright, so in the very last bit, what we've got a line, we've got B, E, and D. We want to find out what E is, so we can show that OE is going to be the same as, so go from O to E is the same as going OD plus BD. OD is just going to be 0 minus 4 minus 1. B was the point, let's go back up to here, right back up to the top, so 6 minus 4, 5. So BD is minus 6, 0, and minus 6. So that's plus minus 6, 0, minus 6. So OE is the vector minus 6, minus 4, minus 7. So therefore E is minus 6, minus 4, minus 7. We finally want to show that that's on the plane, so show E is on 2x plus y, take 2z equals minus 2. Substitute that into there, 2 times minus 6 plus minus 4, take 2 times minus 7. equals minus 12, take 4 plus 14, which equals minus 2, and therefore it's on the plane. Therefore E is on, oops, it's on the plane. And there we have it, all done.